I'm going to share.
Perfect.
Okay. Is that okay? Do you see the full screen mode?
Yeah, looks perfect. Yes, we can see you and hear you loud and clear.
Okay, excellent. Well, thanks again, Klaus, and hi everyone. So this presentation is going to be about dynamic congestion pricing and reinforcement learning. Agenda is first rationale and description for this project. Then I will describe the design of the controller solution using reinforcement learning, discuss the results, and provide an overview of conclusions. The rationale for this work is something you are probably familiar with, which is traffic in roads. It is generally a very serious problem in most metropolitan areas across the world. And there is a need for action in multiple fronts, including the following three. So first of all, it is necessary to optimize, because building more roads that satisfy the pace of demand is not sustainable. Second is introduce mechanisms to motivate drivers to consider alternate routes and to change their usage schedules. And third is that it is necessary to create new sources of revenue for investment in public transportation. And a mechanism that fulfills these three action areas is dynamic congestion pricing. And the essential idea is to put a price for using a road, and not only put a price for it, but also make it dynamic, depending on the level of congestion of the road. This is not something new. It has been implemented in several places. In Singapore, it has been working for years. It is actually a dynamic congestion pricing system. It started as static, but turned into dynamic. In London and Stockholm, it is a static congestion pricing system. Static means that the price structure is not real time, and it's set on a fixed schedule system. Interesting thing is that in Singapore it started like that, but they realized that they needed to change it to dynamic. In New York City, just announced a few weeks ago that they're going to deploy congestion pricing within the next few years. And in highways in Canada and the US, there are several dynamic congestion pricing implementations already working. In fact, the one you see here in the picture is in Miami. The idea of this project is to build is to use reinforcement learning to build a dynamic congestion solution with the hypothesis that this is going to be a better solution than the existing ones. And for this, we started with a simple road system in order to contain complexity, and this road system consists of 2 no toll lanes, free lanes, and 1 free lane. And obviously, working in this type of project, it is not possible to test with a real road system, so it is necessary to use a road simulator, and we use the Sumo road simulator, which is an open source system developed by the German Aerospace Center. In this project is to design a control mechanism, a controller that monitors road conditions, and based on this information produces a toll price. And this toll price is communicated to drivers using a display system in the road drivers read this information, make a decision on which route to use, whether to use the toll road or the free road. And this decision from drivers modify the road conditions, which in turn changes the monitored information that inputs the controller. The controller gets new information, recalculates the price, and so on. So this controller needs also to maximize some operational targets. And in this particular example or case, we want to maximize two targets. One is to the total flow across the system. So this is the flow of cars. Flow is the rate of vehicles per unit of time. So the rate of vehicles in the free lanes and in the toll lane. We want to maximize that. In addition, we want to also maximize the total revenue from the toll lane. This is the same as maximizing the flow in the toll lane. Other targets could be added. So, for example, there are some deployments that look at fuel consumption targets and emissions targets. But for now, in this work, we just use these two flows. In order to evaluate our solution, we need to compare it against the existing methods. The majority of the deployed existing methods, at least the ones that are documented, there's not a lot of documentation about this type of system. But what we found is that most of them are using basic feedback control techniques. And this example illustrated here shows that the essential ideas of using basic feedback control. In a feedback controller, what you want is to, in this type of controller, you want to regulate an output signal and try to make that output signal the same or as similar as possible as the input reference signal. In this example, the controller is going to set a price, and the monitor signal, the monitor state information, is the density in the toll lane. The density, because density of traffic. Density is the level of the concentration of cars or vehicles in a road segment. So it measures the density in the toll lane, and it compares it with the reference density. And this is the reference density that is given to the operator knows that at this density, the toll lane will operate without congestion. So the task of the controller is to set a price such that the output is going to be as close as possible to the reference input. And to that, it needs to compare these two quantities. They're just a simple subtraction, the target minus the actual density. This produces an error. The error is the input to the feedback controller. And the feedback controller runs a very simple control algorithm, which is called on-off type control. Some people call it bang-bang control. And here, if the error is less than 0, is negative, then you increase the toll price, because the reason is that if it's negative, it's because the measured density is higher than the target density. So if you want to lower congestion, you have to increase the price so that less cars take that route. And if it's positive, then you decrease the toll price. This type of approach has some limitations because it is necessary to have these values, these reference values, and they are difficult to obtain. And even if you obtain these values, they may not reflect good road conditions. So it is not. It depends on a lot of measurements that don't necessarily reflect the target goals. Additionally, this works only with one state variable, and in many cases you need to optimize and work with multiple state variables. And finally, this is these basic feedback methods do not include optimization evaluation. So you don't know if what you're doing is optimal or is very good or is mildly good and so on. So you need to do a lot of measurements and fine-tuning to figure out if what you are getting in terms of results is good or bad. So this is what we want to improve through reinforcement learning. So the proposed solution is a reinforcement learning controller. So it's also a feedback controller, but in this case the controller is a reinforcement learning agent. And this approach was pursued to address these disadvantages mentioned before, but also because if you look at this problem, it is very dynamic price setting. It's a sequential decision problem. So you have a controller that is making decisions at every control interval and with the idea of maximizing some objectives. And this is a classical sequential decision process problem, and these are the type of by reinforcement learning. The other reason for using reinforcement learning is that it doesn't require setting this target example before. You just need to set the optimization targets, and these optimization targets are described through a mathematical function, which is the reward function. I will talk about that in a moment. And additionally, reinforcement learning includes optimization. And this is a key aspect because the reinforcement learning agent is continuously measuring its performance towards the optimization goals. It's measuring how good or bad are the results with respect to the goals that have been specified through the reward function. So, part of the design was to split the problem. The reinforcement learning controller is dealing with two things, and we decided to split those two areas of scope and deal with them separately. The first stage, is a reinforcement learning controller that optimizes the way how to split traffic between the free lane and the toll lane. And this is a purely traffic dynamics problem and can be entirely handled with the Sumo simulator and the reinforcement learning controller. And this has been the main focus of this project. But the goal of the controller, as we recall, is to produce a toll price. So we need some function that converts from a split rate to a price. And this is a toll price function. This can be solved in multiple ways. It could be an open loop function, analytical function. It could be also a feedback controller that could be implemented using either basic feedback control or also reinforcement learning. In the initial stage, we use an analytical function. So this toll price function is just an analytical function that uses an estimate of something called the value of time. And we will see more about that in a moment. Another advantage of this approach is that it enables future scenarios where the road controller has direct communication with the vehicles. So it's not necessary to have this indirect display mechanism in the road. So if you foresee, for example, road systems where there are connected cars or autonomous vehicles, the road controller could be negotiating a price dynamically without involvement from the driver, and will be able to determine what exactly a price based on the fraction of cars that decide to buy access to the road. this could be done in multiple ways. One of them is using auction mechanisms. So the solution architecture for a reinforcement learning problem is basically an implementation of the reinforcement learning framework. And I assume, because of the nature of your group, that you're familiar with the basic reinforcement learning. Cover it as a refresher. So a reinforcement learning framework environment, which is what we want to optimize, and the agent that runs the reinforcement learning algorithm. And the agent needs to be trained interactively by interacting with the environment. And this interaction basically is observing the state of the environment, performing an action, observing the change of state and the provided reward, and updating incrementally a policy function. And this policy function is such that given a state, it produces an action. So the agent interacts with the environment and incrementally improves the policy function. And the policy function has to be such that it should maximize the sum of rewards across the time that the environment is operating. So this in a nutshell is what reinforcement learning does. So this project, what we did just map this into an actual architecture. And for this, the environment is implemented as a combination of the simulator, the Sumo simulator, and another software module that implements the highway system that we are working with. And the reinforcement learning agent implements the reinforcement learning algorithm. And there is additionally the open, the direct function for calculating the price. Thus is not part of the feedback loop, but it requires input of part of the state, the speed information. The state and the reward and the handling of the action, all of that is defined in the toll road environment module. So that the role of this module here is to manage traffic generation. So it generates the traffic. It collects measurements from the simulator, and these measurements are the state information. It executes routing decisions based on the split ratio that was provided as an action here, and it based on the action that was just executed. In reinforcement learning, it is necessary to define several information components. Some of the first three are part of the data model for communication between the reinforcement learning agent and the environment. So these are the state, the action, and the reward value. The reward value is very simple, it's just a real number. And it's also necessary to define the reward function. The state definition, so the state is are the characteristics of the environment that are observed by the reinforcement learning algorithm, by the reinforcement learning agent. For a road system, it is necessary to identify which are the most descriptors of traffic in a road. And the two main metrics for that are concentration and speed. Concentration is sometimes referred to as density or sometimes referred to as occupancy. And there's a mild difference between them, but in general, both density and occupancy are forms of concentration. In our project, we use occupancy. So when you hear me talk about density or occupancy or concentration, I'm meaning the same thing. And you see here, these are classical traffic diagrams, and they are important in the following sense. if the x-axis is the occupancy, the concentration, and something very important in terms of flow is that flow is going to grow up to a certain degree of density. Above that, there's going to be too much cars, too many vehicles in the road. They will start interacting too much with each other, and the traffic will slow down. And if the traffic slows down, the flow slows down. This is the graphic of speed versus occupancy. So you can achieve maximal speed, which is called free flow speed, up to a certain level of occupancy. After that, the occupancy will be too high, and you will start to see decreasing traffic condition. So, key point here is that the two main measurements are occupancy and speed, and we will measure both of them for both the toll lane and the free lanes. And the fifth dimension is the input rate flow, and so this is our space vector. The action definition. So the action we need for the first controller. Remember that we split it in two: the split ratio controller and the price controller. The split ratio controller needs to produce an action which is a ratio between 0 and 1. And we need to determine whether this is going to be continuous or it's going to be discrete. Because of the algorithm that we chose to use, which is double DQN, that algorithm only handles discrete actions. So the range is discrete values between 0 and 1.0 with increments of 0.1. But we went a step further to simplify, and this was because this produced better results. Is instead of having a range of 10 or 11 actions, depending on whether it's starting 0, 0.1, we had just 3 actions, which were increments in the split ratio. So the actions were decrease the split ratio by 0.1, increase it by 0.1, or leave it the same. So the split ratio output, the action output, may look like something like this, staircase type of signal like this. The reward function is perhaps the most important design decision in a reinforcement learning project. It is the task that requires more trial and error. So this is in my experience, there is still a lot of work to be done to find good methods for designing reward functions. There are some heuristics, but I think that there's still a long way to improve how reward functions are specified in order to be able to spend less time in this task. So the operational targets are two, the total flow and the revenue, or in the toll lane, which is the flow in the toll lane. I work with variations of two types of reward functions, two types of equations. The first one is a linear combination of the total flow and the toll flow. The total flow is the toll flow plus the main flow. So a simple linear combination will be the main flow plus 2 times the toll flow. This type of reward function did not give us very good results. Maybe didn't try enough, but decided to go to another type of reward function, which is the toll segment flow, and with a penalty, which is the length of the queue entering the toll lane. And here's a better view of that. So you can see here that if this is the toll lane, this is the main lane, and you try to maximize the flow of the toll lane, but you are not cautious about the congestion level in the toll lane, you may start to have vehicles queuing up in the entrance to the toll lane. And the vehicles that are queued here are vehicles that are not going through the free lanes. So this is going to diminish, it's going to decrease the total flow. So you want to totally avoid having a queue in the toll lane, because those vehicles that are queued there can easily go through the main free lane. Also, you don't want to be charging a toll and then experience a queue. You want to have good quality of service because you are paying for it. So this is something that you totally have to avoid. So that's why, in the end, this proved to be a much stronger and good reward function. And so it has, again, a component which is a reward, the toll flow, and a penalty. Penalties are expressed as negative values. And we are not using the length of the queue, but we are using the delta in the length of the queue. So that is the current value of the queue minus the value of the queue in the previous interval. A reinforcement learning algorithm used, as I mentioned before, is double DQN. It's an enhancement to deep queue network, or DQN. I started with DQN, but did not get very good results, so moved to double DQN, which produced very significant improvements. And unfortunately, don't have time in this session to go over the design and the characteristics of double DQN. But this is a description of the characteristics of the network. Double DQN uses two sets of neural networks, and each set has two stages of 36 nodes each, and these are the characteristics of the neural networks. As you, if you have worked in reinforcement learning problems, this is a common way of evaluating whether you are achieving a solution or not. So you use a learning curve. The learning curve episode reward. So if you see that the reward is improving as you increase the number of episodes, then it means that you are learning. This type of problem requires very slow training. It requires about 650 episodes to train. Each episode has 20 steps. So about 1,300 reinforcement learning steps to train. I mentioned that because there's something that is a little bit difficult with this type of problem, is that the simulator, the Sumo simulator, because it's a micro simulator, simulates every vehicle and every aspect of the road. If you put too many vehicles in the simulation, it can become a little bit slow. And so if it's slow, each of these runs is going to take a long time. So this work can slow down a little bit. So this is an area for future work, how to speed up the simulator, explore other simulators. This is not something that we have done yet, but I think it is necessary to do. So how do we evaluate whether the solution is good or not? Well, compare it against a feedback control solution. And this solution is similar to the one I just described, but instead of measuring the density in the toll lane, we're measuring the Q delta in the entrance of the toll lane. And the reference value, and so this one was run for different load levels, and the finding is that the reinforcement learning solution is produces results about 7.7% in average higher than the basic control solution. And this is with loads ranging between 65 and 90% of the road capacity. So this is a good, okay result. It is not huge, but it demonstrates that it's possible to get reinforcement learning algorithms that do better than the basic control algorithms in terms of this type of metric, the total output value. But then we measure some other things. And the other measurement is the quality of service. We measure as the Q in the input toll lane. Quality of service, because if you, as I said before, if you have queues, you have bad quality of service. If you don't have queues, you have good quality of service. And very interesting thing is that for the reinforcement learning controller, the DQN, double DQN controller, there are no queues up to 86% capacity of the road. So it behaves perfectly. Not only it produces more throughput, but it also does not have any queues, so it has very high quality of service, as opposed to the basic reinforcement, basic feedback controller that starts building a queue at about 35 to 40% of the input capacity, which is not very good. So you start having very long queues with the basic controller. So this is a clear and significant improvement with the reinforcement learning algorithm. And why is this happening? And this is a very interesting demonstration of the power of reinforcement learning. The reason why, and this graphic here, it shows the throughput, the output at the toll lane. So the blue is the double DQN, and the orange is the basic feedback control. As you see, the basic feedback control tries to fill the toll lane completely. The maximum capacity for that at 100 steps is 2,900 vehicles. So it performs the goal of maximizing the flow in the toll lane, but unfortunately, maximizing the flow running at 100% capacity causes queues. And the reason for that is that the road systems are stochastic systems. They have probabilistic variations. So if you run at maximum capacity, there are going to be spikes in the behavior of the system, and then you're going to have queues. The very nice thing is that the reinforcement learning controller learns to avoid running at maximum capacity, because it knows that if it runs at maximum capacity, it will violate the queuing, the queuing component of the reward function. So it clearly learns that. It has a price for that. The capacity, the throughput in the toll lane is not as good, but it's not too bad. And at the same time, it has no queue, or it has queuing up to a very high input rate. How is this deployed in an actual system? So let's say that we have a model for the toll price function. We have the reinforcement, we have a model for the split rate controller. We have an analytical model for the toll price function. So let's say that we deploy this in an actual road system. We have a monitoring system that collects the metrics, the occupancy and the speed, and then we feed that to the controller. The controller produces the split ratio, passes it to the toll price function, which produces an estimated price. That price is displayed in a variable message sign, and the drivers are going to make decisions. But the challenge here is that those decisions have to be such that the ratio of cars going through the toll lane versus the ratio of cars going through the free lanes has to be the same as the ratio here. And for that to happen, we need to have a very good toll price function. And the toll price function is something that is a different beast. It's something that depends on socioeconomic information. It depends on the level of income of the drivers, of the travelers. It depends on the behavior, the social behavior of the drivers, and a lot of economic factors. And these factors are summarized in a metric which is used in transportation. It's called the value of time, which is the amount that a traveler will pay or is willing to pay in order to save time. And it is possible to, so the function we're using, it is possible to extract the price given the value of time and given the split ratio, and also given the speeds, the different speeds, because the value of time needs to be taken, considered with respect to the value that the traveler sees. If the traveler sees that there is a high speed on the toll lane and a low speed in the free lane, then it is going to say, okay, I'm going to save a lot of time, and my time costs so much, so it's going to make a judgment on that. So I won't take much time on this, but this is just a way of doing it. It may not be the best, as I said before. This may require doing also a reinforcement learning controller here, or doing just a feedback controller that adjusts the price based on the actual ratio that it is finding. Conclusions. Well, first of all, this was an exploration on whether reinforcement learning could be good for dynamic congestion pricing. And the initial results are that we think that yes, it is possible to obtain good solutions. They can be improved through fine-tuning and through choosing different reinforcement learning algorithms, improving the reward function, but this is a good start. This also, we found that this simple toll road system is a good starting point to work on dynamic congestion pricing. If you start with a very complicated road system, with an urban road system, the simulation problem can become so complicated that you are dealing with so many challenges at the same time. It is difficult to make progress. We make progress, we believe, because this problem is kind of like a hello world of dynamic congestion pricing. And another key point is that in order to do this type of work, it is absolutely necessary to have traffic simulators like Zoom, because you cannot do this with real roads. You need to simulate. And not only you need a simulator, but you need a simulator that has a control interface. And this is something that Sumo provides, and that is quite important. I saw other simulators, but they didn't have APIs. They only have GUIs, graphical user interfaces, so they were not useful for this task. And as I said before, this problem is computationally demanding, and this is basically because of the computation level of the Sumo simulator, or for that case, any microscopic simulator. It would be really good to have a simulator that has parallel execution. And finally, these methods not only provide a better solution, but they also can inform how to improve basic feedback controllers. And this is actually what happened in our case. Initially, we tried multiple basic feedback controllers. We didn't get good results. And finally, when we found the solution for the reinforcement learning controller, it gave us an idea to use the input Q as the reference metric, and that gave us a very simple solution for the feedback controller, which could be fine-tuned and improve. So these are reinforcement learning controller brings a lot of value because it's an optimization technique as well. And I said before, basic feedback control does not have optimization. So that is the presentation. And I don't know if we have time for questions. But
yes, thank you very much, Mauricio. It was a very nice talk. We are a bit late, but maybe if there are some urgent questions, we can try if it actually works. So anybody has a...
Yeah, if you sit and talk loud enough, it should be good. Clear and loud.
Yeah, I will try to start video here.
Yeah,
okay.
Please, go ahead.
Essentially, that system should have learned, if I understood that well, you correct me if I'm wrong, a function with one input parameter and one output parameter. That would be interesting to plot it. So whether it is complicated or linear or whatever, because I see that's like you have one thing that's the price or the split ratio, and the other thing is the congestion, or let's say the free flow, or the reward. So that would be an interesting thing to see, like how that.
The state was a bit more complicated, but Mauricio.
Sorry. Yeah, the state. No, there was more than one state variable. There was only one state variable for the basic feedback control method, but for the reinforcement learning method, there were actually 5 state variables.
Maybe 5.
Was that related to your question? I'm sorry.
You have been talking about only one, so it would have been interesting to see what the others are. But then a graph doesn't work.
So let me briefly show that. So the 5 state variables are the speed of the toll segment, the speed of the main segment, the occupancy of the toll segment, occupancy of the main segment, and the input, the flow rate.
Okay.
Another question?
Sure.
Yeah.
Did you compare double DQN against a random agent? And my second question is, did you do an ablation analysis on the hyperparameters?
I repeat the question. Did I compare the double DQN against a random agent?
Yes.
No, I didn't. I only compared against the basic feedback control. But I did, in the end, a random agent, if you look at the learning curve, because in double DQN or in DQN in general, you start with a very high exploration rate. So at the beginning of the training, you are basically using a random agent. So in that respect, yes, it's a comparison. This is the territory of random actions. Because if you look at the characteristics of the reinforcement learning controller, of the exploration starts with probability 1. So initially, for some time, everything is exploration. That's a random agent. Then this has a decay rate, so that the exploration starts to decay up to a minimum probability of 0.06, and it decays at this rate. So I think, yes, this is part of what the training of double DQN does. I didn't catch the second part of your question.
Basically, how did you choose the hyperparameters on this slide?
How did I choose these parameters?
Yes.
Could you say again? I didn't completely hear.
For example, how did you choose the learning rate or the neural network architecture?
Yeah. Well, that's basically by trial and error. This is part of what this is. I mean, as far as I know, there's no shortcut for that, like in most machine learning problems. You have to start with some estimate based on your experience and based on similarity to other problems, and then go from there.
Okay, I think in the interest of time we have to move on. Thank you very much. Let's thank the speaker.